Assalamu alaikum, dear students. We're back again. Let me give you a quick recall of what we've studied last time. So if you remember, we were talking about mechanical waves the most. We said there are two types, and these are longitudinal and transverse wave. And also, we've mentioned that mechanical waves need a medium to travel through. Without a medium, they cannot travel through. We said when it comes to transverse wave, the particles of a medium vibrate up and down, or you can say at right angle, perpendicular to the direction of wave travel. On the other hand, we have longitudinal wave, where the particle of a wave or the particle of the medium vibrate back and forth parallel to the direction of wave travel. And of course, we've learned about the diagram or the shape of each wave, and we can also said that even a longitudinal wave can be represented by a sine wave as well, but you have to be really careful in that case. The first thing you need to check is the y-axis for any wave that you're given. If it is written displacement, that wave it is going to be for a transverse wave. But if on the y-axis is written maximum pressure or density, or just density or pressure, that sine wave, of course, is going to be for a longitudinal wave. All right, now before going to the new topic here, I would like it to give you, for example, a question or perhaps one or two, and then tell you there's basically a new idea. What if you got a question like this in Wizari? So of course it is best to be prepared for this one here. So what we have is one of the questions here. It says a wave traveling in the positive x direction as shown in the figure. First part of the question says, what type of a wave is it? And then what is the speed of a wave? So how do you answer a question like this? Okay, so we've mentioned that the first thing you need to look at once it comes to a question like this is you'll have to check the y-axis for the diagram that is given here. So if we're going to look at this one here, or this y-axis for this wave here, right? So what do you notice now? Just zoom in this one or make this one a little bit bigger. Okay, I think that's too much, but it's all right. So the first thing that we have, as you can tell here, it is written displacement here. We said whenever it is written displacement for this wave, it is obviously going to be a transverse wave, right? Because if it is longitudinal, it would have been maximum pressure or just pressure or density here. Okay, so now we know this thing right here. So we know that this is a transverse wave. So now we can, at this point, of course, cancel out two options here, because these are says longitudinal. Now we know this is a transverse wave. So it is either going to be option A or option B here. But how do we know, for example, so now this is a transverse wave, how do we find the speed of this wave in here? Now we've learned that speed of a wave, it is equal to V, the captive frequency, times the wavelength, right? What am I writing? Frequency times the wavelength in here. So now it is obvious, how do we measure the wavelength, Baba? Watch this. Now we know that the distance from this point to this, that is one wave, right? But what is given here is the distance between, you can say, of three consecutive crests in here, which is, this is one wavelength, and of course from this point to another, that is going to be two wavelengths now. So we can say two wavelengths together, it is equal to 4 meters, as you can see here. What about the length of one wavelength? You could divide both side by 2, so one wavelength, it is equal to 2 meters. That is one of the things that we found. So now we have the wavelength. The next thing you need to do is you'll have to find the frequency. Is the frequency is given? The answer is no. But can we find the frequency? Absolutely yes. So how do you do that? You know that, okay, watch this one here. We know that the time for one full oscillation, that'll be the period, right? And of course, if we have the period for one wave, we can, using the period, we can find the frequency. So bear with me here. So starting at any point you want to, for example, you can see that this one is starting from 0, then this one is 0.2 second, this is 0.4 second, and then it continues on and on here. But do we have to know all these times that are given? No. Okay, you just need the time for one full wave here. What is one full wave here? You can start at any point, but if I start from 0 here, this is one full wave. So how much time does it take for one full wave? That is 0.4 second. Yes? Can I say this is the period of the wave? For 0.4 second. Yes. So once you do this, Now, remember, that'll be the second thing here. The period, it is for one full wave, it is 0.4 second. Basha, if we have the period, can we find the frequency? Yes, frequency, the kata 1 over period. So it is going to be 1 over 0.4. So what is it equal to now? That is going to be 2.5 hertz, we can say one, yeah? So that is going to be 10 divided by 4. That is 2.5 hertz, Basha. Now that is the frequency we found, Basha. You can find the frequency for any, starting from any other points. That is totally fine as long as you're taking the time for one full wavelength. Once again, this is 0, this is 0.2, this is 0.4, and that is 1 period. Okay, so now we know that the frequency we just found, which is equal to what? It is equal to 2.5 hertz times each wavelength, it is 2 meter, right? So now 2 times 2.5, so now we can say the wave speed, it is equal to what? It is equal to 5 meter per second here. All right, so now we know that this wave is transverse and the speed is 5 meter per second. So which one of these is correct now? It is going to be option A right here. Okay, so this is one of the questions you need to be aware of, because don't be surprised if you're given period as, let's say, on the diagram. So that is also something possible. You could do that here. All right, we could solve this question too, by the way, just in case this is for sound wave here, but I would let you try this. Perhaps we have, or you can give it a try, or I'll solve this one for you later. That is related to chapter 4 here, but it's the same as the concepts that we've studied in chapter 3. So you should be able to solve this one on your own as well. If not, we'll just solve it together. That'll be later. Okay, now. All right. So now let's jump into the new concept here. The new concept that that is going to be chapter 3, section 4. It is about wave interaction here. So now we know that waves interact with one another, right? Just like, for example, any other objects here. But there's a difference in the interaction of physical objects and waves as well, let's say, or not physical objects, let's say any other objects that are not waves compared to waves as well. Basha. So let me give you an example. As you can see here, these things that you see here, for example, on a surface of water, these are called bumper boats, right? Just like, for example, these bumper cars, or these cars that you ride, for example, in these, let's say, fun cities or whatever you call them, right? Or these malls, that they have these electrical cars, and of course you collide with other, for example, with your friends and colleagues maybe. All right, so what exactly happens once these bumper boats collide? And once they move head on and then they collide, of course, they're going to bounce back, right? Of course, each one of them in a different direction, let's say here. So this is how things are, we can say, normally. When two things collide, especially if there is a rubber in between the two, or for some reason if they're elastic, they'll just collide, and then especially for those kind, they're just going to rebound or separate and move in opposite direction here. The goal of saying this is this, or the aim of this is this: no two bumper boats can exist at the same point or at the same location, at the same space, at the same time here. So these bumper boats cannot exist at the same space here. Just like, for example, when you're at some place, now you're occupying this space here, so no other person can occupy this space right here. Okay? Don't say, what if, for example, a person goes on top of the other person here on their shoulder? No, we're not talking about this one here. The space you're occupying here, it cannot be occupied by any other things here. But is it the same thing with waves? No. Waves have something different. For example, when we have two sound waves here, they can, for example, once they move head on to one another, once they reach one another, they're not going to, for example, just collide and bounce back or move in a different direction. No, they can just pass through one another. And that is the beauty of waves, you can say. So waves, we can say, unlike other objects, they can actually, or indeed, pass through one another. And then after they pass through one another, they could just, every wave can go on their own without being affected afterwards here. But what will happen once they, for example, overlapping or passing through one another, of course, it can be added or subtracted. And that is what is called wave interference. And that is what we're going to study for today, inshallah. So let me remind you what I've just said, like once more, like a recap here. We said no two bumper boats can occupy the same space. Why? Because these are physical, right? Once they collide. But for waves, they can actually move through one another and then just continue going, like on their direction or whatever they're heading to. But of course, once they are passing or moving through one another, this process is called wave interference because they're going to interfere with one another. So these two waves are going to add up or be subtracted from one another, and that is called wave interference here. Okay, so what do you need to know here? Remember to go through this one here. What is the most important parts are this part and this part here, which is italic, as you can see here. It says two different material objects, all right, cannot or can never occupy the same space at the same time. But for waves, it is different. Two waves can occupy the same space at the same time. That means two waves can exist at the same space at the same time, unlike bumper boats right here. And for example, we have a lot of examples here, and this would be one example. So these are two waves. These are made by a device that is called a ripple tank, by the way. So it is just a tank that produces or has a device that produces these ripples, and ripples means waves, by the way. So two waves, you can see that these waves are interacting here. At some points, you can see the waves get bigger, and some other points, the waves get smaller, and these are the topic of today. So this process that we have, or the next thing that we have, it is called superposition. What is superposition here? It's almost like actually, it is like when two waves interfere with one another, they overlap, or once they overlap, they superpose, right? What does that mean? That means once they are passing through one another, their displacement, or you can say they'll interfere with one another. So they're going to add up or be subtracted from one another, and that is what is called superposition. So we can say superposition, it is the, combination of two overlapping waves here. You can say not just two waves, it could be more than two waves, by the way. So superposition, it is the combination of two or even more overlapping waves. When we say overlapping waves, that means one wave is over the other, or once they're passing through one another. We also have something else that is called superposition principle now. So there is superposition, that would be the sum of, or the combination of two waves, let's say, or could be even more, okay, that are overlapping or interfering, passing through one another. Basha, what is the principle of superposition? Here's the principle, all right? The principle of superposition states that when two waves, okay, are passing through, let's say, the same medium, whether, like for example, could be opposite or in a different, let's say in a different direction here, okay, in a different direction, once, for example, they superpose, okay, so the displacement of the resultant wave, it is going to be the algebraic sum or the sum of the individual waves here. So this is what is called superposition. Now I'll draw some diagram just to help you understand more of this one here. So once again, it is when two or more waves meet in the same medium, okay? When two or more waves meet in the same medium, of course, we can say the displacement of or the same medium, the displacement of the particle of the medium, that would be the resultant displacement, of course. It is going to be what? It is the result of the displacement of the individual, or you can say the combination or the sum of the individual waves here. What exactly do you mean by this? So now consider we have a wave that is going to the left, and here's the first wave, you can see that here. And we also have another wave, but this wave, it is moving to the right. So what do you think will happen once these two waves meet at a certain point here? Let's say these are the two waves, or perhaps let's just move them here. So this is one of the wave that is moving, okay? We're getting closer and closer at this point here. You can see that. What happens exactly when these two waves meet at this point here? You can see that these two waves are, one of them is above the equilibrium, Okay, one of them is above the equilibrium, the other one is below the equilibrium. So if you ever want to find the total amplitude or the total displacement for the particle here, let's say one of them it is 3 upward, that is +3, the other one is -3 downward. So the result of this one, it is going to be 0 at this point here. But you know that these waves are continuing to move when each one of these in opposite directions. So at this point here, if this wave continue, for example, to move, let's say at some point it might get right at this point or right at this location here. Now we can make this one a little bit to this point here, or perhaps draw something better than this, just so that these two will match. So now at this point here, these two are both overlapping, and we can say their displacements are the same side. So if each one of these are 3 and 3, so this is 3 and this is 3, so these are both +3 and 3 here. So the total of this two, it is going to be, this would be the resultant of this two right here. So this is going to be the resultant of this. And what about the ones that are below? It is also going to be combined, but downward here. These two are going to be combined upward, so it is going to be a total of 6 here. Let's just assume that. Okay, and these two are also going to be combined here, which is going to be 6 downward here. So this is what we mean by adding or the combination or the resultant wavelength here. So let me repeat one more time. Superposition principle, it is the combination or the sum of two or could be even more overlapping waves. That is the first thing. The second thing, we have the superposition principle. It says when two waves meet, Baba, so their amplitude would be combined, Basha. So if the amplitudes are on the same side, we add them together, Basha. If the amplitudes, even if they are both, so if both are up, we add them. If they are both down, we add them, as long as they are on the same side. But if one of them is up and the other one is down, then of course we're going to subtract them. For like the resultant here, it could possibly be something, or it could be 0 as well in here. This is what is the superposition is, or the superposition principle is about here. All right, now, but there's one thing you need to know now, and that is this: superposition principle happens with every kind of wave. It is not just sound waves or water waves. It can happen with every kind of waves, we can say, including electromagnetic waves too, Basha. So there is this point, which has been in Uzadi as well, by the way. So this is important. You need to know this, Basha. Okay. Let's zoom out this a little bit. So superposition, of course, it can happen, right? Or can apply to all kind of waves, both mechanical and electromagnetic waves as well. But what do you think will happen after the two waves will pass one another? Then every wave will go back to their original shape, and then they'll just go back to normal, and then they keep going towards their destination there. Okay, now that is all about regarding superposition principle. Now, at this point here, okay, so once these waves are meeting at a point and their displacements are combined here, that is called wave interference. Don't forget, there are three types of wave interference, Basha, and we have something called constructive, Basha, constructive interference, where when two waves, for example, meet, the resultant displacement will add up. And then we have destructive interference. For destructive, of course, it becomes two categories. We have complete destructive, where two waves, they have the same amplitude. Once they move in opposite direction, they cancel one another out. Maybe you don't have any idea what I'm saying, but just be patient. In a second, I'll draw the waveforms so that you can have a better idea of what I'm saying. And then there is the second type of destructive is, we can say, weakening destructive interference. In that case, of course, the two waves are not going to completely cancel out, but they'll just cancel out partially here. Okay, so let's talk about these three types of interference here. The first one we have, okay, is constructive, and then after that we have destructive. But in destructive, of course, it can be two types. So we're going to talk about each one of these. Constructive interference, by the way. Okay, and then there is destructive. Destructive what? Destructive interference. All right, but don't forget, in destructive, there are two types, okay? Oh, not this one. In destructive, there are two types. Okay, in destructive, there are two types. one of them, let's just start with complete actually first. Complete, destructive, and then there is weakening, you can say. Or you can say partially cancel out. So what do I mean by constructive? Okay, so once again, we have two waves. This wave, it is moving to the right, and then there is another wave that is moving. Okay, let's just copy paste this. Perhaps it might be a little bit better so that we can see what happens exactly afterwards. Okay, so here's the next wave that we have. Now we have these two waves. These are both moving in opposite direction, Basha. So this one is going to the right and this one is moving to the left. So what exactly happens when these two waves meet? Okay, so let's do this again, all right? We're going to copy the whole thing. So now these are the two waves that we have. So notice what happened when these two are both meeting. Let's just move this aside a little. What happens when these two waves are meeting on the same, or let's say at the same place? Let's just bring this one forward a little and this one to here. So once these two waves are meeting at the same point here, you can see that. So we can color one of these actually. Okay, so now you can see here, these two waves are exactly, for example, they have, even if they don't have the same amplitude, as long as you can see that, their displacements are on the same side here. And because their displacements are on the same side, we're just going to add them here. So if we ever say, for example, for constructive, we'll say we have waves that their displacements are on the same side here. So for example, like this orange and blue one, their displacement is both up and here both down. So the resultant is going to be something like this one here. So their displacement are going to be additive here. As you can see here, we can see that the resultant displacement, it gets larger. In other words, we can say that the amplitude of the resultant, it is going to be the amplitude of the first wave plus the amplitude of the second wave here. So of course it is larger than the amplitude of each one of these individuals here. Masha, it doesn't have or it doesn't necessarily have to be the same amplitude. One of them could be 1, the other one could be 3, doesn't matter. As long as these are both up and these are both down, so we just add them here upward, and then these are added upward. So the resultant resultant amplitude is going to be larger than the amplitude of each of the individual waves. Okay, that is regarding the amplitude. What about complete, all right? This is also something interesting here. Okay. So for complete, we have two waves again. These two waves are also moving in opposite directions here, Basha. So let's copy this one again, right? But these two waves, let's erase this one. These two waves are, again, moving in opposite direction here. Okay, let's see if we can, yep. All right, take a look here. What happens when these two waves are approaching one another? Okay, so these two waves, or these are the waves that we have. Imagine, for example, what happens when these two waves are coming right at this location here. You can see that each one of these waves, their amplitudes are, we can see that in opposite direction. So we can see that their displacement, you can say displacements are in opposite direction here. So for the blue one, it is upward, but for the, or I don't know what color is this. I mean, more likely orange, right? Okay, a little, I don't know, light red, whatever you call it. All right, so this one is upward, while this one is downward here. And because they have the same amplitude, like we said, if this is 2 positive, this is going to be 2 negative. And once again, here, the same thing, it is going to happen, right? So as a result of this 2 here, they're going to cancel one another out. So what is going to be the resultant? It is just 0 amplitude. So, but the condition for this 2, by the way, to be a complete, the amplitude of each one of these waves must be the same. Okay? And by the way, you could do that with a pulse wave 2 here. It might be even better, by the way. For example, if you have one pulse here and then one pulse there, perhaps we'll do that with a pulse as well in a second now. But that would be the second case here, which is, and we call this one complete destructive. Why? Because they completely destroy one another, so there's nothing left. So if we ever say, for example, the amplitude or the resultant amplitude is going to be the amplitude of the first one plus the amplitude of the second one, so that is going to be 0. Why? Because one of them is positive, the other one is negative, so the total is 0 right here. So there's nothing left for the resultant here. It is just simply 0. Now, what about weakening interference here? That is also another kind of interference that we have. we can say the displacement of the waves are in opposite direction here, but let's say this is one of the wave that we have, and then there is another wave. Perhaps we could do this one here, right? We can just copy paste on this. All right, but we can make this one a little bit smaller so that you can see the difference between, actually, no, this one doesn't work this way. Okay, we have another wave. Let's just do this one. I'll write it here so that we know whether if it is exactly the same or not. Okay, that is this. As for the all right, so watch this. This is, we can say, the second wave that we have. Okay. Not one of the best, but okay. Should be one part so that we could do this or move this all together. So here's the wave that we have. Watch this. So now we have two waves. So let's move this one now. What happened when these two waves meet, for example? First of all, let's flip this one here. So now these two waves are both moving in opposite direction here. So what happened when these two waves meet? Okay, one of them is going to the right, the other one is going to the left. So what happened when these two waves or waves here meet at this point here or at a point here? So you can see that once it gets right here, these are not what I expected. I'll just draw a normal wave, Kaka. This doesn't work. Okay. So what happened? You saw the wave, right? So here's, let's say, the wave that we have. All right, this is the, mashallah. This is the wave that we have. What happened when this wave, for example, or these two waves meet now? This is how it is going to look like here. Because you can clearly see that these waves do not have the same amplitude here. If this one, let's say this is 3, let's just say, for example, this is going to be 2, right? So now what is going to be the resultant amplitude here? It is going to be 3 minus, or the amplitude of the first plus the amplitude of the second. The amplitude of the first, that is positive 3, we can say plus the other one is negative 2 here. Okay, so what is the resultant now? It is going to be positive 1 here. So the resultant amplitude of this one, if I want to write it here, it's not a good thing. All right. All right, so the resultant of this one now, it is going to be something that looks like this one here. You can see that now this resultant, it is, we can see that it is less than the amplitude of the displacement, or the amplitude of this wave, it is less than the amplitude of a larger wave in here. You can see that these two waves canceled each other out, but not completely. So the resultant wave is weaker now. So we call this one weakening interference. Basha? So this is the bottom line of, you can say, of each one of these. Let's summarize this one here. We have 3 types of interference. Constructive, Gutman, the amplitude of both waves must be on the same side here, whether both up or both down. So we add them together. If it is for destructive, all right, they're going to cancel or destroy one another. The condition is for complete, the two waves, these are both the waves must be on opposite side of equilibrium, by the way. But here, they must have the same equilibrium. So one of them is up, the other one is down. So they fully cancel each other out here. So there's nothing left. We call the complete destructive interference, Basha. And then for weakening, the amplitude of, these are again on opposite sides, but the amplitude of one of them is larger than the amplitude of the other. So they're going to cancel out, but it's not completely. A part is going to be left, which is weaker than the amplitude, or smaller than the amplitude of a larger wave. So we call this one weakening interference. Now, if you remember in the other video lessons where we're talking about the relation between energy and amplitude in here. So what do you think will happen to the energy of this wave as a result of this term? Now, because the amplitude increases, of course, the energy of this wave or the resultant wave, it is going to increase in here. All right, and you do know, or you remember the relation, which is, it is directly with the amplitude square here. What do you think will happen to the energy of this wave now? It is going to be 0 because the amplitude is 0 here. What about the amplitude of this one here? It is not 0, but we can say the amplitude, it is going to decrease because the amplitude got smaller in here. So this would be basically the difference between all 3 kinds of interference that we have. There's a last point that I need to mention. What do you think will happen as these waves pass, for example, now they meet at this point, so but these waves are still going, for example, right? So this blue wavelength, after they, for example, they leave this spot here, now each one of these waves are going to, for example, go back to normal shape. They're just going to, let's say, continue moving the way that they are moving here. So this would be for the black, let's say this orange one here. We could do this one here. So it keeps moving to the left, and this one is moving to the right, and then they're back to their original shape as well. So it is true with the same on each of the other waves too. All right, so let's get back to this one. These are the three types of interference. You could do that with a pulse as well if you want to. All right, with my constructive, destructive, that is, by the way, here I've wrote weakening first, makes no difference. That'll be the destructive in here. My later pulses are on the same side of the equilibrium. You can see these are opposite side and opposite side too. Later, Gutman, displacements have the same sign if these are, because they are on the same side, so they're both up or both down here. Masha, this would be the result of this too. But here, these displacements are on opposite side and opposite side here as well. With my later resultant displacement, it is larger than the individual pulses here, but later it is smaller than, here it is smaller than the larger one, but here it is going to equal to what? Equal to 0 right here. Okay, but the energy, Gutman, is going to be the sum of the two waves. Is going to increase. Energy here is going to decrease. Energy here, because it is total destructive, it is going to become 0. And then after the interference, waves retain their original shapes. They'll just go back to normal. So now, after we've learned about these, all right, so what is constructive and what is destructive interference? We can say constructive interference, Basha, it is a superposition of two or more waves. So that is when two or even more waves superpose or meet at a point, they interfere, right? So of course, in which the individual, we can say displacement on the same side of the equilibrium are added together, Basha, are added together to form a resultant wave where the amplitude is larger than the amplitude of each of the two waves. What about weakening or destructive interference? That is also we can say the combination of two or more overlapping waves, in which we can say, Asha, the individual displacements are on opposite side of the equilibrium, are added together to form what? To form the resultant wave, whose displacement, and the displacement of the resultant wave, it is going to be smaller than the displacement of the individual wave for weakening, and it is going to be 0 in the case of complete destructive interference. Basha, so that'll be the kind of like the explanation of each one of those. Now, there's one more thing you need to know regarding. Now, we can tell whether two waves are going to interfere constructively or destructively just by looking or knowing their phase differences here. So what exactly the phase difference? We can say the phase difference is in a wave, like is the variance of the position of one wave compared to, or you can say of a specific position on a wave, or we can say one wave compared to another, and of course that showing how much one wave is ahead of the other one. So let me tell you a little bit more regarding the phase difference, and then tell you what you need to know in phase differences for these kind of constructive or destructive interferences here. Let's say now we have a wave, Basha. This is one of the waves that we have. And then if I have another wave, okay, this is the second wave that I have. You can see that these two waves, of course, both of them starts at this point, and both of them, let's say these are points. These are crest with crest, trough with trough, and then their ends with one another. So can I say these two waves are moving together? Yes, if they're moving together, none of the wave is moving ahead of the other one here. So in this case, we can say the phase difference, right, between these two waves here, it is 0. Phase difference, right, between these two waves is 0 degree, Basha. And then, of course, we can use a degree here to account for the phase differences here. So we said that this could be 0, this could be 90, this could be 180, and this is 270. If it gets back to the same point, that is also 360 as well. Now, this is regarding the phase difference, Basha. So because these two waves are moving parallel to one another, right? None of the waves leaving behind the other, right? So we can say the phase difference between the two waves is 0. Okay, now the next thing that we have, if we have a wave like this, for example, here's one of the wave that I have, and then I have another wave which is exactly opposite to this blue wave here. So now you can see that whenever the crest of one wave overlaps, let's write crest and crest here as well, Basha. These are both crest and these are both trough. And of course, you could write different colors so that you can see that these two are matching as well. So we have crest and crest. These are trough and trough, right? These are together, so the phase difference is 0. But for this one here, all right. So, but for this one here, that is the crest of one of them. Let's just write this in blue, crest. All right, and this is, we can see that the trough of the other one, trough. And you can see that one more time, that is the crest of this black wave, and that would be the trough of the other. So we can see that whenever the crest of one wave, it is overlapping, it is right above the trough of the other wave. At this point here, we can say that the phase difference, it is 180 degrees. The phase difference, it is 180 degrees in here. Now, where does this 180 degree comes from? You can see that if you extend, for example, this black wave in here, like if you go back to the origin of this one, this would be the initial or the beginning wave of this one, right? So now, isn't that half a wave ahead of the other one? Yes, and half of a wave ahead of the other one, that means it is 180 degrees. Let me just give you a little bit more information, even though you don't need that. If two waves start at this point, we said the phase difference between the two is 0, right? What about if one of the waves started at this point here? That was a little bit above. Okay, these are, by the way, you might not need to, but as a general information, if one of the waves starting like this here, so you can see that it is, one of the wave is 90 degrees ahead of the other one here. So that'll be the beginning. So this is the 90. If, by the way, you can divide a wave into 4 different sections, right? So if this is 0, this would be 90, this is 180, this is 270, and this is going to be 360. Like if you go by the degrees in here, 360. So if we start at this point, so we can see that this wave is 90 degrees ahead of the other one, but you're not going to see this part here. What about, for example, if a wave starts at this point, the one that we just saw, okay? So this is for 190, that was 90, wasn't it? What about for the 180 that you just saw? For example, this is one of the wave, and this is going to be the next wave. If it's starting like this, you can see that starting like this below, that is starting, or the phase difference, the angle phase difference between the two, it is going to be 180 degrees, Basha. What about if one of them, it is starting at this point here, right? And then the other one starts right at this point. Something like this, that's not a wave. Okay. So starting like this point here, something like this. And of course, this one, or starting at this point here, that is the phase difference between this two, it is going to be 270 degrees. And if you want to trace it back, this is how much this wave is ahead of the other one, right? That is 180, this is a 90 here, so the total of 270 ahead of the other one. And then if it is one, like for example, if it is going to start at this point, you can say 360 or 0 degrees. That'll be the phase difference between the two. But you might say, Mr. Do I need this? No, the only thing that you need is, Baba, this one here. It is either 2 cases, Basha, in phase and out of phase by 180 degrees. What do I mean by this? We said it is either this case, the above one, where crest overlap crest and trough with trough, all right, Basha, that is the phase difference is 0 degrees. And the other one here, where the phase difference is 180, Basha, it is when the crest of one, it is overlapping, it is right above the trough of the other one. Later, the twanin blend, the phase difference is 180 degrees. So what is the purpose of studying this now, in this case, Baba? Look, if you have 2 waves, for example, once the question tells you the phase difference between the two is 0, that means the 2 waves are overlapping. They are both up or could be both down, Basha. Yeah, Basha, if these 2 waves are, for example, crest with crest, trough with trough, so would that lead to a constructive interference or destructive interference? We're no longer going to study, for example, weakening. I mean, we could do that too, but the purpose here, would that be a constructive or destructive? So at any point here, when the phase difference is 0, okay, phase difference is 0 degree, that means the two crests are together, the two troughs are together, so it is always going to lead to what? To a constructive interference. Basha, this is the purpose of studying the first one right here. What about the second one? Now, for the second one, for 180 difference, we know that once we have two waves, all right, this is one of them, and then this is, okay, this is going to be the second one, right? So whenever the question tells you the phase difference, even without showing you the diagram here, when it says the phase difference is 180 degrees, that means the crest of one is overlapping the trough of the other one. These are right above one another. Abash, if you have a case like this, once they interfere, is it going to be constructive or destructive? Of course, you know that these are going to be destructive. If the amplitudes are the same, what will be the resultant? 0. Agar amplitude كانش same nabu, awkati is going to be weakening interference. Yani amplitude will be less than the amplitude of a larger wave here. Okay, so that is the only thing you need. You don't need anything else. If you learned about the extra information, that would be great. Again, don't worry about that one. All right. Of course, you're going to need that one later. So this is, you could say, or the parts that you need here is going to be this part where the two waves are in phase, or you can even say this one here. If you have two waves, these are in phase, you can consider that. So crest with crest, trough with trough, so it is going to be constructive, and this one is going to be 180 different, so this is going to be destructive interference. Oh, Idika, it is extra. All right, now we have a few questions here. It says, using the superposition principle, draw the resultant wave of each of the example below. Of course, you're not going to draw waves in Wazari, but the resultant will be given. They'll give you this two, for example, and they'll give you a bunch of options, says which one of these is the resultant. But because these two waves are not exactly on one another, overlapping, so how do we know if these are going to be constructive or destructive? So at this point here, you can see that the best option that you could do, Baba, is use a ruler and draw a straight line. These are the two waves, Baba, wave A and B here. Once you draw a straight line, you can see that the crest of this, it is overlapping the crest of the other one. Yeah? What about the trough? So the trough is 2. And then one more time here, so you can see that is continued. So isn't that the same as if these two waves are overlapping one another? Yes, if that is the case, so what do you think will happen to the resultant? Of course, the resultant, it is going to be larger than the amplitude of each of the individuals. I think this color is not that visible. We'll just go with black maybe. All right, so this is going to be the resultant wave in here. So in other words, this is going to produce a constructive interference. Basha, what about the next one here? Watch this. Do the same procedure. The crest of one, draw a straight line here, okay? And that is, the crest of one, it is overlapping the trough of the other. And this one, trough with crest one, yeah? So what do you think will happen now at this point here? Immediately they cancel one out here. So you can see that if these two waves, watch this, this is the, we can say equilibrium one, yeah? If this is positive 2, this is going to be negative 2 here. So they're going to, negative 2. These are going to completely cancel each other out. So the resultant is going to be 0 amplitude or 0 displacement here. So this is constructive and this is a destructive interference. So always bizani baba, crest with crest, constructive, trough with crest, that is going to be destructive. Come on here. Section or chapter review question says what? Says, what is the difference between constructive and destructive interference? Well, but the difference is very easy. But for constructive, the two waves are moving in opposite sides, so their displacements are on the same side of equilibrium. So they are both up or both down together. So that, of course, would lead to a constructive. What happened to the resultant wave? The resultant displacement, it is going to be the combination, the sum of the two waves, which is obviously going to be larger. What about for destructive? We said the displacement of each waves are going to be an opposite side. One obviously is up, the other one is down. Then these two, of course, are going to be subtractive from one another. So the resultant amplitude or the displacement, it is going to be either smaller than the larger wave, or it is going to be zero in the case if they have the same amplitude. But later, the light destructive interference, so we could just say the resultant displacement, it is always smaller than the displacement of the larger wave. While we cannot just say the resultant displacement, it is smaller than, for example, the displacement of the two waves here. Not necessarily, Basha. What do you mean by this? So it is always mandatory, if you're ever saying smaller, you have to say smaller than the larger wave, because not sometimes it could be different here. So what do we mean by this one? Let's say we have a wave. The displacement of this one, it is 6 centimeter or 6 meter, doesn't matter. And then we have another wave that is in opposite direction here. Okay, this one is just, let's say 2 meter. Basha, once these two, for example, are going to cancel each other out, what would be the resultant displacement here? The resultant is going to be 6 minus 2, it is going to be 4, right? So here's 4. All right, but is this 4 smaller than this 2? Obviously not, but is it smaller than the amplitude of the larger wave? Yes, so that is why it is always best to say it is always smaller than the amplitude of the larger wave. You cannot say smaller than the amplitude of the two waves. These are very easy, but it looks very confusing, Basha. The question says what? It says which of the waveforms or waveform shown below is the resultant waveform. But let me tell you a secret of solving this question here, right? Even though you could give it a try yourself, and it would be best if you know. Once you're given a question like this, Baba, always start or look at a point or a part out of a wave where all the waves are on the same side. For example, at a point like here, this one here. Because we said that when the waves are on the same side, what will be the resultant of the, or what is going to be the resultant, Baba? I get two wave if they are both on the same side, the resultant wave, it is going to be larger than the amplitude or the displacement of either the two waves, Basha. And these two are added together, they form this one here. So see, now we can see that this red one here, which is obviously Y3, so Y3 is going to be the resultant wave. I hope you understood what I was saying. I'll repeat, Baba. So always look at a point where the two waves are on the same side, because if they're on the same side, we've mentioned earlier, if the displacements are on the same side, the resultant, it is going to be additive. So we add the displacement or the amplitude of these two, so we get a resultant which is larger than the displacement of either the two here. So this Y3 here, it is going to be the resultant. Basha, can we look at other parts? Yes, of course. You can look at this one here too. All right, you might say, what if I look at a different location? Well, that is totally fine, but it is the easiest when you look at these parts where all of them are on the same wave. So this wave, it is, let's say at this particular point here, this might be, let's just consider this as positive 3. What about this one here? This might be negative 3. So as a result of this two, one is up and one is down. These two cancel out, so you get something like 0 here. So now this is also an indication that it tells you this red wave is the resultant wave here. Okay, that is the answer to that question. Now we have question 31 says, can more than two waves interfere in a given medium? Absolutely yes. All right. So far we've been talking about two waves interfering, right? But more than two waves can also interfere, because we said, according to superposition principle, when waves meet at a point, the resultant displacement, it is going to be the sum of the displacement of the individual waves. We'll subtract from the other waves here. So yes, multiple waves can interfere in a given medium. So waves, unlike we can say matter, can occupy the same space at the same time, allowing their displacements to be algebraically combined to create a resultant wave. Getting at the next ones, and I need you to fully understand this. But let's say, what is the resultant displacement at a position where destructive interference is complete? All right, it says destructive interference and also says that it is complete. So when do we have destructive interference? All right, this time let's use a pulse instead of a full wave. So we have a pulse that is going here, right? And then there is a pulse that is going, let's say, to the right, and then there is a pulse that is going to the left. Once these two pulses meet, one is up, one is down, and in order for these to be complete, they must have the same displacement or amplitude here. If this is +3, this is going to be -3. They both cancel out, so the total, the resultant, it is going to be what? 0. All right. So once again, the resultant displacement is going to be 0. 0, it's a 0 meters, 0 centimeter, it doesn't matter. You can say 0 unit of length. Okay, 33 says when two waves interfere, right, can the resultant wave be larger? Can be larger than either of the two original waves? Yes, the resultant can be larger only, right, if the interference is constructive. Have you understood the question, what it's saying? When we have two waves, whether this is one and we have another wave, right, moving in the opposite direction, doesn't matter. Can the resultant wave be larger? Can the resultant wave be larger than the either or the amplitude of either of the two waves? Yes. If these two waves both are interfering constructively, resultantaka, it is going to be the addition of the two here. So of course, this resultant, it is going to be larger than the displacement of either of these two waves here. Now, here's another part. So the second part of the question, so now that is the answer to that question would be yes. It says, if so, under what condition, that's halatachi, the amplitude of the resultant is going to be larger under constructive interference. هذاك اللي بسالبته like can it be smaller than the amplitude of either of the two waves? The answer is yes. Under what case? Under complete destructive, because if it is going to be smaller than both of the two amplitudes here, it must be constructive. What if we, for example, what if one wave is way larger than the other one? So unlikely it is going to be weakening interference. The resultant might be still larger than the amplitude of the other one. All right, so just don't pay much of it. Actually, yes, think about what I just said, and hopefully you'll understand that. It's not that difficult. All right, the next thing that we have, it is reflection of waves here. Okay, now what happens, for example, when a light falls on a surface of a mirror? Of course, light will be reflected, yes or no? And once you, for example, stand in front of a mirror, you're getting ready, like to go to school. What do you see, like on a mirror? Of course, we're in a mirror, let's say, you'll see a reflection here. So what exactly or why do you see a reflection? Because light from you hits the mirror and then gets back to you, and this is how you see your reflection. So in other waves, or the point of saying this, waves get reflected. Okay, now, how do we explain this one here? Or what do we have in here? Now, the things or the reflections that we have, it is, we can say we have two cases for reflection at this point. All right, so let's split here. Okay, now there is a pull, a light pull here. We have two pulls, and then there is a string. Okay. There is a string here. But for one of them here, there is a ring. I think I drew too much here. Oh, we can't erase this. We'll move this one instead. So for this one here, there is a ring that is attached here, and this one, it is fixed. Okay? So we can say this is free boundary. Let's not forget free boundary. Boundary. On this one, we can say fixed boundary. You can call it free end, fixed end, doesn't matter. Boundary, that'll be the end. So now these are the two types of, so what exactly happens? Okay, and this is, by the way, it is about reflection or wave reflection. Wave reflection. So what exactly happens once we send a pulse on a wave? Just a pulse, right? This pulse, of course, it is going to move forward, yes? After the wave is moving forward, this is how it is going to go. All right, it is keep going forward until it reaches this point here. Once it reaches this point now, as the wave is approaching this, right, this ring, because it is free, it is going to move up with it, right? All right, so now this two here, right, are going to move together, or this one, right, moves up and up until the wave, for example, the wave is going here until it reaches maximum displacement. The wave will be reflected now, so this ring, it is going to move up. I think I don't like this diagram here. I'll just do manually or bare hand, let's say. So now as this pulse, it is approaching, okay, as this pulse is approaching the end in here, now this pulse, because it is upward here, it is going to make this ring move upward here. So this ring, it is going to move up and up and up until it reaches this point here, and that is where the wave reaching here. This ring, let's draw something perhaps like this. So this is where the ring is at this point here, Basha. And then after that, after now it went up. This ring here, or this free end here, it is going to move down here. As it is moving down, so now there will be, this pulse is just going backward here, but on the same side of the equilibrium here. I think it's not supposed to be this detailed though. Just remember this. Let me make it shorter for you. I don't like once I give too much details here. Just remember this, Baba. As the pulse here, it is approaching the end. This this ring here, it moves upward, right, once, and then after that it comes downward, and this pulse here now, it is going to be reflected the same way that it came here. So this is the pulse that went, and it is going to be reflected the same way that it came. And you can see that, we can say that here the wave is reflected. The wave is reflected. Okay, now what about this one here? Once we send the pulse, okay, once we are sending a pulse, once we're sending a pulse here, this pulse, it is going to get to this point right here, okay? So once it gets here, this wave is trying to make this point move upward just like the ring, but because it is fixed, it cannot move upward here. So as a result, right, this wave trying to apply a force on this fixed, you can say tut point or whatever, right, upward, but it doesn't work. As a result of that, or as a reaction of this point, it is applying a force downward on the wave. So now the wave is going to be what? It is going to be reflected, but also it is going to be upside down here as well. So we'll say what happens here is the wave is reflected, and it is also inverted too. Or you can say upside down. All right, so this is what happens here. What about here? Is the wave upside down? So no, so we can say the wave is only reflected but not inverted. Okay, so that'll be the key between the two reflections that we have. Let me give you a short summary of what I just said here. Waves get reflected. There are two types of wave reflections here. One of them, it has a free boundary, a free end. It has a ring, so it allows this rope to move up and down with it here, with the wave, let's say, so that the wave get reflected, but it is not inverted. All right, that is a reflection at a free boundary and free end. And then the second type of reflection that we have, it is when the end is fixed, right? Remember, the end, or you can also say that the particles have freedom or maximum freedom, or the particles here can have maximum displacement. What do you mean by maximum displacement? That means this ring can go up and down, of course. Isn't that a displacement? Yes, but here, the particles, once a wave reaches this point, because this is fixed, even if with this wave trying to make this point move up, but it cannot. So the displacement here, for this point, it is 0 at this point here. Don't forget. So what happened when the pulse reaches this point? Again, it applies a force on this point up, but it doesn't work because it is fixed. This point is a reaction of that. Okay, Newton's third law, for every action there is an equal and opposite reaction here. So this point applies a force on the pulse here, which makes it move downward, and now the pulse is reflected back in here. But that is not the whole thing here. So here got reflected and inverted. So the next point, that is happening, or that is important, which is this. If I ask you what is the phase difference between these two, what will be the phase difference? Now guess what happened when these two waves meet, for example. Of course, once they meet, right, this is moving to the right, OADK moving to the left. Let's just write this one a bit nicer, or maybe we can even move these two waves together. Let's just move them here. Okay, that is one of the waves here, all right, and this is the other wave. Okay, what happened when these two waves meet, of course, because, or maybe something before that. What is the angle or the phase difference between these two waves? Are these two waves both up, both down, one, yeah? Both up, one, yeah? So if I want to ask for the phase difference, what is the phase difference between these two? The phase difference is going to be 0, huh? Do you remember we said if it is crest with crest or trough with trough, the phase difference is 0. That is, so the phase difference is 0. What about these two waves once they meet? One of them it is up, the other one is down. So what is the phase difference between the two? By the way, we assume that no energy is lost. So the amplitude of the wave that is going, it is going to be the same amplitude that is coming back for both cases here. So even the drawing perhaps is not perfect, but the amplitude of these two waves are exactly the same. But you can see this is crest and this is a trough. So these are on opposite sides. So can I say the phase difference between these two are, right? The phase difference is 180? Yes. Yalla day. Good man. If the phase difference is 0, or if the two pulses are on the same side, would that be a constructive interference? Excuse me. Would that be a constructive interference or destructive? A constructive. Well done. So the resultant of this, it is going to be a constructive what? Interference. Oh, that's a lot to write. Okay, what about this one here? That is going to be destructive interference. Destructive interference. Okay, now, what would be the resultant of this one? We can say that would be number 5, the resultant amplitude, okay? It is going to be the amplitude of the first wave plus the amplitude of the second wave, because these are both on the same side, which is going to be larger than the amplitude of either of the two waves here, yeah? What about the resultant amplitude in here? The resultant amplitude, it is going to be 0. Why? Because it is total destructive interference here. Now remember, we assume that no energy is lost, so the amplitude of the reflected wave is exactly the same as the one that is going. So the resultant amplitude, it is 0. Or you can say amplitude 1 plus amplitude 2, it is 0 because the second amplitude is going to be below. So one positive, one negative, they cancel out in here. So what about the energy? If I ask, the energy of this wave increases while the energy of this wave, it is going to decrease. But the next thing, if I ask what will happen after the two waves or the two pulses separate, then each one of these are going back to their, let's say, normal shape, and then they'll just walk away from the scene or that place that happened here. So that is the difference between the two type of reflections that we have. One of them, it is called reflection of a wave at a free boundary, OADK Gutman, fixed boundary. We have a string here, a rope or whatever. There's this ring here that allows it to move freely up and down here. Well, this one, you can see that it is fixed, so it doesn't have the freedom to move or to be displaced here. Here, once the pulse is sent, all right, this pulse, it is reflected, but it is not inverted. It doesn't become upside down. It's just coming back the same way that it went to. So the phase shift, it is 0 between the two. Later, Gutman, the pulse is reflected, but you can see that the reflected pulse, the one that is coming back, it is upside down. So we say it is inverted too, both reflected and inverted. You can see that the reflected pulse, has the same amplitude as the incident pulse, and this one has the same amplitude as well, but it is in opposite displacement, or you can say it is in opposite direction, below the equilibrium. Phase difference صفر, phase difference 180. Basha. When these two waves meet, when the incident and the reflected pulses meet, what will happen, Baba? Gutman is going to be constructive interference. Later, it is going to be a complete destructive interference. The crest of one aligns with the trough of the other one here. The resultant displacement at the boundary here, it is maximum, don't forget, at the boundary, Basha. What do you mean by the resultant displacement is maximum at the boundary here? Baba, when this pulse gets this one here, it makes this this ring move upward, but how much upward? By the same amount of the amplitude of a wave. So this is maximum displacement because this one is going to move up, the way it is going to move back to the same point. So here you can call this one maximum displacement at the boundary here. But later, but man, the boundary is fixed, so there's no displacement, or you can say the displacement at the boundary, it is 0 because it doesn't move up or down at all here. Okay, the next thing that we have, right, that is point, we can say number 6, right? We can say point number 6, there's no restraining force at the boundary. But because it is a ring, so the pulse makes it move up and then back to its place. So there's nothing to restrict that, to stop that motion here. But away the boundary, why does the pulse gets inverted too? Okay, that is because of this one here. Okay, the resultant or the boundary exerts, we can say, an equal and opposite reaction force, and that is Newton's third law. If you ever wonder why the pulse is reflected, this pulse, it is trying to apply a force upward, but because it doesn't, so this boundary applies equal and opposite force down on the pulse. This is why the pulse, it is switching side or becomes inverted here. Okay, and then an example would be a pulse or wave pulse in a rope attached to, let's say, a loose ring or the whip's end. You can say this is exactly what I mean. An example would be a rope that is tied to or rigidly to a wall here. These are the examples of the two types of reflections that we have. Whenever we have a free boundary, always when the two pulses meet, they will always be constructive. Once we have a fixed boundary, there's always going to be destructive, complete destructive interference actually, because we have questions later. For example, if a pulse send, but if the end is free, then what will be the resultant of the two waves once they meet? That is constructive if the end is free. But then if the end is fixed, rigidly attached to a wall, the pulse that is sent and the pulse that is reflected, these are on opposite side, so it will always lead to a destructive or complete destructive interference. Basha, the last thing that we have, it is standing waves. I think that'll be enough for this session. Next time, inshallah, we're going to start with standing waves. Basha, till next time, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.